You know, the world can feel pretty chaotic, right? Customer rivals, project deadlines, it all just seems totally random. But what if I told you there's a hidden order to all of it? That even randomness has a shape we can actually use to our advantage.
So let's dive right into that. How do we even begin to predict the unpredictable? I mean, that's the fundamental challenge for any business, any planner, really anyone trying to get ready for the future. You can't know exactly what's going to happen, but, and this is the key, you can understand the range of what's likely.
And here's the secret. Randomness isn't just noise. It has a structure. And smart businesses, especially in fields like logistics and finance, have learned how to find these shapes in their data. We call them statistical distributions, and they are the absolute key to turning all that uncertainty into a powerful tool.
Okay, so let's start with the undisputed superstar of statistics, the one you've for sure seen before. I'm talking about the famous bell curve, or as it's officially known, the normal distribution.
This one's called the most important and most widely used distribution in statistics for a reason. Its nickname, the bell curve, comes from that unmistakable symmetrical shape. And you find it pretty much everywhere in nature and in data.
Now this slide might look a little intense, and yeah, you might spot some text in another language. Just ignore that for a second. Let's focus on the graph itself and how we can tweak its shape. A bell curve is really just defined by two numbers. First, the mean, which sets the center or the peak of the curve. And second, the standard deviation. Think of that as the width of the bell. A small one, like that sharp green curve, means your data is all clustered tightly around the average. A big one, like that wide black curve, it means everything's much more spread out. The amazing part is, just by changing those two numbers, we can model all sorts of different scenarios.
And hey, this isn't just some abstract theory. Think about it for a sec. Test scores in a huge class, the heights of people in a country, even tiny errors in scientific measurements, they all tend to follow this beautiful bell shape. It really is everywhere you look.
All right, let's switch gears. We're going to go from the most common distribution to maybe the simplest one there is. Our next shape is the discrete uniform distribution, and this is where every single outcome is equally likely.
You know, the name really says it all. Uniform means every possible result has the exact same chance of happening. There's no favorite, no peak in the middle. It's just a level playing field for every single outcome.
The perfect example, rolling a fair six-sided die. It doesn't matter if you're hoping for a 1, a 2, or a 6, each number has a 1 in 6 shot. It's that simple. And that's the uniform distribution in action.
And this comparison just makes it crystal clear. On the left, you've got the bell curve, with that obvious peak showing you the most likely result. But on the right, you see the uniform distribution. It's just a flat line. This visual tells the whole story. One has a favorite, and the other one treats all outcomes as equals.
Okay, that's great. But what happens when you don't have perfect historical data? What if all you have is, a best guess? Well, that's where our next model comes in handy, the super practical triangular distribution.
See, this is what's called a rough approximation. And honestly, that's its superpower. When you don't have perfect data, but you can make an educated guess about three things, a minimum, a maximum, and the most likely value, you can build this simple but incredibly powerful model. Just look at this graph. It's so intuitive, right? You have A, the minimum value, B, the maximum, and C, the mode, which forms the peak of the triangle. So in our example here, T369, we're basically saying the value is going to be at least 3, at most 9, but it's most likely to be 6. And what's great is that it doesn't even have to be symmetrical, which is perfect for messy real-world estimates.
And trust me, this is used all the time in business. How long is a project task going to take? Well, what's the best case, the worst case, and the most likely case? Boom! That's a triangular distribution. It is the go-to tool for making a structured guess, which is absolutely crucial for budgeting and setting realistic timelines.
All right, for our final shape, we're shifting from measuring continuous values to counting how often things happen. Let's take a look at the Poisson distribution, which is a fantastic model for the frequency of random events.
So what this distribution does is help us answer questions like, hey, what's the probability we get exactly 5 customer calls in the next minute? It's absolutely perfect for counting events that happen independently but at a known average rate.
Now, there are a few key conditions to use this model. First, you have to be counting events. Second, those events need to be independent. One phone call shouldn't make another one more or less likely to happen. And third, you need to know the average rate, and that rate has to be pretty steady. And the business applications for this are huge. How many emails will your server have to handle in the next hour?
How many call center agents do you need staffed at 3 p.m.? The Poisson distribution helps businesses predict demand, which is all about matching your resources to that demand, and that is a core challenge for any service business.
So we've journeyed through 4 pretty different shapes of uncertainty: the bell curve, the flat line, the triangle, and the counter event. But so what? After all that, why do these models really matter?
It's because they do exactly what you see right here. They take that foggy, chaotic, confusing mess of uncertainty and they give it a clear shape. They turn it into actionable insight.
And ultimately, that's the goal. This isn't about predicting the future with 100% certainty, because that's impossible. It's about understanding the shape of these random events so we can all make smarter, more informed, data-driven decisions. It's about replacing a wild guess with a calculated risk.
So as we wrap up, I want you to take a look around your own world. From the number of customers at your favorite coffee shop to the time it takes you to commute, these patterns are everywhere. The only question left is, what part of your world could you model next?